The backbone of algorithmic efficiency, mastering data structures in modern programming. In the realm of computer science and software development, data structures form the foundation upon which efficient algorithms are built. Whether managing vast datasets or optimizing real-time applications, understanding how different data structures function is crucial for any programmer aiming to write high-performance code. This guide delves deep into the world of data structures, exploring their types, operations, and practical implementations across various programming languages. From arrays and linked lists to advanced constructs like graphs and trees, we'll uncover what makes each structure suitable for particular tasks and how they impact overall system performance. Fundamental concepts in data structure design. Data structures organize data so that it can be accessed and modified efficiently. The choice of an appropriate structure depends heavily on factors such as access patterns, storage requirements, and computational complexity involved in performing common operations. At its core, every data structure revolves around two primary functions: insertion and retrieval. These basic operations determine how quickly data can be added to or extracted from a collection, influencing everything from database queries to search engine indexing mechanisms. Time complexity measures how execution time increases relative to input size, commonly expressed using big O notation. Space complexity evaluates memory usage based on input size, indicating trade-offs between speed and resource consumption. Understanding these metrics allows developers to make informed decisions when selecting among competing implementation strategies, ensuring optimal balance between efficiency gains and hardware constraints. Evaluating array versus linked list implementations. Arrays provide contiguous block storage where elements are indexed sequentially by numeric positions. This design enables constant time access but limits dynamic resizing capabilities due to fixed capacity limitations inherent in most language implementations. Linked lists overcome array shortcomings through nodes containing both value and pointer references. While offering flexible growth potential, random access operations become significantly slower compared to direct index-based lookups available in traditional arrays. For example, inserting new items at arbitrary locations within an array requires shifting subsequent elements, a linear time operation, while similar insertions in singly linked lists only require updating node pointers, achieving near constant time complexity under certain conditions. Choosing between these two fundamental structures hinges largely on application-specific needs regarding frequency of modifications versus read operations required during runtime processing cycles. Trees and graphs. Hierarchical data organization. Trees represent hierarchical relationships through parent-child connections, enabling structured navigation paths essential for many file systems and organizational charts found in business environments worldwide. Binary trees restrict each node's children count to a maximum of 2, facilitating specialized traversals like pre-order, post-order, and level order methods used extensively in sorting algorithms and expression parsing routines. Average tree depth impacts search performance dramatically. Balanced variants like AVL trees maintain logarithmic height ratios, guaranteeing predictable worst-case scenarios regardless of dataset characteristics. Graph theory extends beyond simple hierarchies toward complex networks, modeling social media interactions, transportation routes, or even protein interaction maps analyzed daily by bioinformaticians globally. Hash tables. Accelerating search through key mapping. Hash tables use hashing functions to map keys to specific indices within underlying arrays, allowing rapid lookup times typically approaching 0.1, assuming minimal collisions occur during distribution processes. Collision resolution techniques include chaining via secondary data structures and open addressing schemes utilizing probing sequences when target slots remain occupied by other entries. Dynamic resizing becomes necessary once load factors exceed predefined thresholds, triggering rehashing procedures that redistribute existing contents across larger table sizes while preserving integrity of stored associations. Selecting hash functions carefully minimizes clustering effects that could degrade average case performance over extended periods despite theoretically ideal asymptotic behavior assumptions made initially. Queues and stacks. LIFO/FIFO principles in action stacks implement last-in first-out principles useful for implementing recursion stacks, browser history backtracking features, or undo/redo functionality present in numerous graphical user interfaces today. Queues follow first-in first-out discipline critical for task scheduling systems, printer spoolers handling queued print jobs, or breadth-first traversal approaches applied in graph exploration contexts frequently encountered in AI research domains. Differentiated implementations exist ranging from simple list-based solutions to optimized DEEC structures providing bidirectional access without compromising temporal guarantees promised by classical FIFO/LIFO models. These foundational abstractions often serve as building blocks for higher-level components requiring precise control flow management while maintaining clear separation between sequential logic layers. Advanced topics. Heaps and priority queues. Heaps maintain partial ordering properties, ensuring highest priority element remains accessible atop heap structure irrespective of internal arrangement changes caused by repeated insert/delete operations. Max heaps prioritize largest values at root positions, whereas min heaps reverse priorities accordingly depending on application requirements specifying desired ordering semantics. Heapify process converts unsorted collections into valid heap configurations in linear time complexities, making them indispensable tools whenever need arises to repeatedly extract either minimum or maximum valued elements efficiently. Applications span widely, including Dijkstra's shortest path algorithm leveraging priority queues implemented through binary heaps alongside Huffman coding employed for lossless compression standards adopted internationally. Practical considerations when selecting appropriate structures. Performance benchmarks vary drastically across different platforms, necessitating careful profiling before finalizing choices, impacting long-term maintenance costs associated with legacy codebases subjected to frequent updates. Language-specific optimizations influence actual runtimes observed empirically. C++ STL containers differ substantially from Python's native implementations regarding memory footprints allocated internally per instance created dynamically during program execution phases. Concurrency considerations arise when shared resources must be accessed simultaneously across multiple threads, risking race conditions unless protected adequately through synchronization primitives integrated properly throughout implementation lifecycle stages. Memory fragmentation issues persist, particularly problematic in embedded systems constrained physically yet expected to handle substantial volumes processed transiently without sufficient cache space available locally. Real-world applications across industries. Data structures power modern technologies from web search engines indexing billions of documents hourly to recommendation engines suggesting personalized content tailored specifically towards individual preferences cultivated implicitly through behavioral analytics frameworks. Social network analyses rely heavily on graph databases storing trillions of relationship records representing friendships formed organically amidst global populations interacting digitally every second since inception decades ago. Financial institutions utilize B-trees for maintaining ordered indexes supporting fast query responses vital for stock market transactions occurring continuously throughout trading hours, monitored closely by regulatory bodies imposing strict compliance mandates. Healthcare informatics employs tree structures accelerating medical diagnosis processes, comparing patient symptoms against extensive knowledge bases compiled historically from clinical trials conducted worldwide, contributing progressively to evidence-based medicine practices embraced universally now. Emerging trends shaping future developments. Rising demands for distributed computing architectures have spurred innovations surrounding consensus protocols requiring sophisticated state-machine replication mechanisms operating reliably even amidst network partitions threatening consistency guarantees otherwise assumed implicitly. Quantum computing introduces novel paradigms challenging conventional wisdom established over past several decades concerning information representation, fundamentally altering expectations regarding feasible problem domains solvable tractably within reasonable bounds defined arbitrarily subjectively according to prevailing academic discourse norms currently dominating research agendas. Multimodal datasets composed jointly from textual descriptions combined with visual imagery demand hybrid approaches integrating disparate modalities cohesively represented effectively using tensor decompositions rather than simplistic vector embeddings previously favored predominantly amongst natural language processing communities exclusively focused solely upon linguistic representations hitherto considered sufficient independently. Edge computing deployments emphasize lightweight implementations favoring compact formats minimizing bandwidth utilization while maximizing responsiveness achieved through localized decision-making empowered sufficiently by reduced latency experienced. Inherently due proximity maintained deliberately between endpoint devices communicating wirelessly through low-power communication channels designed intentionally for intermittent connectivity patterns characteristic primarily within Internet of Things ecosystems expanding rapidly nowadays. Conclusion: data structures are integral to developing scalable, performant software solutions applicable broadly spanning diverse industries relying increasingly upon digital infrastructures facilitating day-to-day activities seamlessly perceived intuitively without explicit awareness of underlying technical complexities masked successfully behind polished UI experiences engineered meticulously considering human-computer interaction best practices rigorously tested iteratively refined, continuously improved incrementally over successive product releases. By mastering key concepts related to choosing right structures aligned precisely with domain-specific requirements coupled consistently with thorough empirical validation ensuring robustness against edge cases arising unpredictably sporadically during operational lifetimes, programmers empower themselves becoming capable architects designing resilient systems adaptable flexibly responding gracefully evolving technological landscapes shaping tomorrow's digital frontier collaboratively co-created collectively through sustained innovation driven relentlessly forward propelled ceaselessly upwards ever striving toward greater heights achievable only together united harmoniously working synergistically interdependently reinforcing mutually enhancing contributions reciprocally enriching shared goals pursued passionately relentlessly. HTML